Greetings, physicists. This video will be about how to solve problems that involve torque and moment of inertia. So we've got a guy trying to push open a door that's stuck, and we know where he's pushing on the door, and we know at what angle, and we know how hard, and we're just trying to calculate his torque, and then later we'll be trying to maximize his torque. So let's draw this. We have the door hinged on the left side, and he pushes at a 20-degree angle away from being perpendicular. So I'm going to draw a little perpendicular dashed line. That's perpendicular. He's 20 degrees away from that, so be careful that you label this properly. If you label it away from the door, that's from the parallel to the door. All right, 20 degrees that way. We can label his force as a 240 Newton force. That's an F. Important. And the point he pushes is 0.75 from the hinges meters, which is a delta x, but really we're going to use it as a radius for this problem. So our torque equation, torque equals R cross F. So we can only use the perpendicular component of his force, and that perpendicular component is this right here. Or if you want to draw it on this side, it's adjacent to the angle. So we would do a cosine. This would be the cosine here. And be careful. I know in the lecture video we said sometimes they call it torque equals RF sine theta, right? But that was because in the lecture video the angle I was using was this one. Was on between the parallel and the force. And the angle they gave us said 20 degrees from being perpendicular. So if you want to avoid that kind of problem, don't memorize RF sine theta, just memorize R cross F, and know that the cross means we can only use a perpendicular force, and then you're just solving whatever triangle they happen to give you. And in this case, they happen to give us an adjacent. So in this case, it will be RF cosine theta. So the R is 0.75 meters, the force is 240 newtons, and we're doing the cosine of 20. So, put it in the old calculator. 0.75 times 240 cosine 20. Now, if you are still in radians, change back to degrees. Radians are going to be once the object starts moving. If we're going around a circle and we're measuring angles around the circle, then it's all angular quantities, then this is we would go back and use radians. But they gave us a degrees, and this is a linear force. And because it's a linear force, we're going to use degrees for this. I know that's confusing. We're just going to have to get used to it. All right, and the answer my calculator spits out is 169 Newton meters of torque. Newton meters. This looks like a 2 sig fig problem, so I'm going to round that to 170. Right there. Perfect. So that's the first question. What torque does he exert? He exerts 170 Newton meters of torque. How could he exert more torque? Well, I can see 3 ways. He is not pushing at the very edge of the door, so if he increased the radius, then this number will be bigger, and he will get more torque out of it. If he pushes harder, assuming he can push harder than he's pushing, then the force will go up. Or if this angle were closer to, in this case, the cosine of 0 would be maximum. So he basically has to, if he tilts his force, instead of pushing this direction, if he pushes straight with those same 240 newtons, he will actually get more torque out of it. Okay? Any of those will work. And if he wants real max, he should do all 3. All right, moving on. Pictures. Pretty straightforward. One big wheel spinning around the center where we kind of expect it to. And we want to max, let's see, which one of the forces, keyword, largest positive torque on the wheel. Now, I will remind you that in a unit circle, when you are starting a unit circle, you start here and you go around in the counterclockwise direction. That is considered the positive direction on a unit circle. It will also be considered the positive direction here. So we will be considering the largest torque that causes a counterclockwise rotation. So if you choose a torque going the opposite way, you're technically choosing a negative torque. All right, some things we can eliminate right off the bat. C. Force C is acting on the pivot point. So it's not going to cause this thing to spin one way or the other. It would cause it to translate if the wheel wasn't held down. It could move the wheel across, but it wouldn't spin the wheel. And by the same token, D is not acting at the pivot point, but D is in line with the pivot point. So D will also not cause a torque on this object. All right, now let's look at the others. I'm really only interested in positive torques. And positive, again, is this way. So E is a positive torque. And then if you look at A would not be positive. A would cause a torque in this direction, and B would cause a torque in this direction. So E is really the only choice if we're going by which is cause the largest positive torque. Now, if, just for your edification, notice that E is at a full radius away with one force. But B is a half a radius away with twice the force. So those are technically producing equal amounts of torque. It's just that B happens to be going in the opposite direction because torque is linear with both R and F. So if I double the radius and half the force, then I get the same torque. So A is technically the most magnitude of torque. It's double the radius and double the force, or it's a full radius at 2 force, which is the most torque of anybody on this diagram. It's just not a positive torque. It would be the largest negative torque. So, good picture, and a little bit of semantics there, in case that ever comes up. Oh, big picture. All right. I always tell you, look for the big picture. We have 2 forces on this wheel. Yes, I see them. And we need to add a third force, and it looks like they're going to give us options. And we want to make the net torque 0. Okay, I gotcha. Here are my options. And I have to apply one of these 5 forces at the point that they've marked P. Well, let's look at the current torque on this system and see what we've got going on. Well, I'm going to look right away at this torque. This force, rather. This force is big. It's twice the force size of the other force there. But it's acting on the pivot point. So there's no torque coming off of this force. So we don't need to cancel that one out. So basically the only torque we have to cancel out would come from this force right here. And if we look, it's about half the size of that big force, and it's acting at 1 full radius. So let me think about this. At point P, I need a force. Point P is half of that radius. So, right, torque is equal to R cross F. So if I half the radius and I want to get the same torque, I'm going to have to double the force. I think. Yeah? Yeah. And it's going to have to cause, so think about it, this force here is causing a torque in this direction. To cancel that out, P is going to have to cause a torque in this direction. So I think the only choice is A. A is the only one there that's twice the size. And it happens to be going in the right direction. B is not the right size, and it would cause a torque. If I put B on there, it would actually go the wrong way. C goes the right way, but it's not long enough. C is the same length as this force, so because it's half the radius, it's not going to cause as much torque. D, if I put D there, it wouldn't cause any torque at all because it's pointing in line with the pivot. And if I put E there, it would cause the wrong direction. So A is my choice. And should be yours as well. All right. Oh boy. There are apparently people who are just crazy enough, or good enough at physics maybe, that they will attempt to walk across very high buildings or across the Grand Canyon on just tiny thin steel cable carrying nothing but this giant pole. So here's like one cliff, and the other cliff's way over here, and there's this big cable in between, and you'll see some dude And then he has this giant pole that he carries. And he walks across it like it's nothing. I don't recommend this. I know my physics, and I still don't recommend this. I don't think it's worth the risk. But anyway, we have statistics for the dude. He's that tall, and he has so he's this tall with this mass. The pole is this long with this mass. And we're looking for his moment of inertia, and we're looking for the rod that he's holding, its moment of inertia. Well, to make this easier, because he may be a uniform shape, although most people are not perfectly symmetrical, but he is certainly not one of the 8 shapes that we talked about in the moment of inertia video. So we're going to pretend that he is. We're going to pretend that he acts like a vertical rod. So what would his moment of inertia be? Well, look where his pivot point is. If he tilts to the left or right, he's going to tilt about that point where his feet are anchored and rotate from there. So he's like a rod spinning around one end of its axis. And if you look on your list of moments of inertia, that would give you a moment of inertia of 1/3 mass times length squared, which for him is 1/3 of 88 kilograms, and his length is 1.8 meters, which we will have to square. So put that in. 1/3 times 88 times 1.8 times 1.8. My calculator says that he has a moment of inertia of 95. What is this? Kilograms and meter squared. Kilogram, meter squared. That's his eye, the eye of the man. All right, well, let's look at the rod. The rod, if it tilts, it's actually tilting about the point where he's holding, which is pretty much in the center. I mean, his hands will be spread out a little bit, but let's model it as being held in the center. So a rod being held in the center, or being spun about its center, has a different moment of inertia. It has a moment of inertia of 1/12 times its mass times its length squared. And for this rod, it had a mass of 20 kilograms, and it had a length of 9.1 meters. Very long rod. So let's put that in the old calculator. 12 times 20 times 9.1 times 9.1. Woo, big one. 138 kilogram meter squared. And I think for both of these, this is a 2 sig fig problem. So this is fine. That's 2 sig figs. I'm going to have to round that to 140 kilogram meter squared. This is why he does it. Remember, the larger your moment of inertia, the harder it is to accelerate you in a circle, or to cause a rotation, an angular acceleration. So he has his own moment of inertia, which is 95, but if you add the rod on top of that, that's like another 1.5 moments of inertia. So he's essentially multiplying his own moment of inertia by 2.5, or close to 2.5, by carrying this rod, which makes him 2.5 times less likely to tip when gravity pulls on him. So if he leans slightly too much to one side, he just kind of tilts the rod back the other direction. And it's more stable than it looks, I'll say that. It's still not something I might trust my life to, but hey, now you know why they're able to get away with it. Okay, last one. Big one. Okay, lights go out. How do they keep the lights on? So some places do have backup generators that run off of gasoline, and they just burn gasoline to turn their generator, which is a bunch of magnets, which we'll get to when we get to electricity. Some of them, so they have gas-powered ones, and then they have this kind, which is a big, heavy disc. So they have a giant, like, concrete wheel. It's pretty big. If I could draw a wheel. And they just kind of spin it up real fast. And that gives it a lot of rotational kinetic energy. And then they can kind of sap that energy when they need to, turn on lights, run the internet, run the phones, so you can call the power company, etc. So, what do we got here? Typical system has a 540, which is wrong. Let me edit that right now, because it's... Oh, no, that's correct. No, I was thinking of something else. Okay, it is 540 kilograms. That's big. That's like 1,000 pounds. A little more than that, I think. Maybe 1,200 pounds. So it's got that big cylinder. So if I'm writing this here, this is 540 kilos. The radius, maybe 1/3 of a meter, 3/10 of a meter. It's thick. And we have a small motor providing that much torque. And we're trying to get it, once the power goes out, we got to spin it up this fast, because that'll give it a lot of energy. And we're asking how long does it take to get there? Ooh, okay. Well, we're going to need a couple things. We're definitely going to need the torque equation. And the torque equal to I alpha. Because that motor is providing that torque, and that's what's going to cause the angular acceleration that gets it up to that speed, and that speed is 13,000 RPMs. But we also need an equation that has speed in it. So let's see. We're going to be able to get I alpha. We're going to be able to get alpha because we have the torque and we have the shape and everything to get I for this cylinder. So we will have alpha. We know it's going to start at rest, so we could say that. Oops, that's not a V. I'm mixing my variables here. Don't mix your variables. Omega naught is going to be 0. It does not start with any angular velocity. And I said meters per second. See, I'm mixing them again. It's 0 radians per second. So we know omega naught. We know omega final. That's this right here. So omega is going to be equal to 13,000 RPMs, which we will eventually change to radians per second so that it matches with everything else. So we'll have omega naught, omega, and they're asking us how long. So we'll be looking for a delta time, is the question. Which, when we know alpha, we can use this equation. It looks like we'll use this one. Omega equal to omega naught plus alpha delta time. Omega naught is just 0, so let's get rid of that. And if we're solving for alpha, we can say that it's going to be equal to omega final divided by delta t. That's my alpha, because I'm dividing by delta t, and I can just plug that in for that alpha. So let's give ourselves some room here. That will make the torque equal to I omega over delta t. Omega is what... No, delta t is what they're asking for, so let's solve for that. And now, when I have variables on the bottom, I immediately get rid of them. I multiply both sides by delta t. I don't like variables on the bottom. They bother me. That'll get the delta t here on top, and then to isolate it, I'm going to divide by torque. So what I will get, all the way down here, is a delta time equal to I omega over torque. And while we're at it, before we start plugging in numbers, let's go ahead and get our I. For a cylinder, a solid cylinder, right, that should be 1/2 mr squared. So this would be mr squared omega over 2 tau. Good. And I know all of those quantities. So the time it takes, plugging those quantities in, it was a 540 kilogram cylinder. The radius was 3/10 of a meter squared. The final omega, oh, we didn't convert that. Well, we can do it right here. 13,000 RPMs. And I have revs over minutes, so I have to multiply by 2 pi. And I have to multiply by 1 over 60, right? Okay. Over 2 times the torque, which I believe was 2.8 Newton meters. Let me check that before I start feeding it into my calculator, but I'm pretty sure that's right. 2.8 Newton meters, okay. All right, so we're just going to shove all that into the throat of the calculator. 540.3, 13,000. Oh, whoa. times 2 pi, and then all the dividing by 60, dividing by 2, dividing by 2.8. Hope I got everything in there. All right, go calculator. 11815. Okay. How many sig figs? 2? Yeah. We can make a case for 2, I think. Gosh. Yeah, all right. I'll do it. So 118, so if I'm rounding to 2, that's 12000 seconds, right? Because kilograms, there's 2 meters here. One of them will cancel. Then there should be a meters per second squared. No, because we're missing a seconds on bottom, and that's when the newtons will cancel. Okay, we're good. So 12,000 seconds. All right. If you divide that real quick, divide that by 3,600, and you get pretty close to like 3 hours. So yeah, that'll take a while to get it up to its operating speed, your flywheel generator. But it will also take it a long time to decay from that speed. And I believe in the meantime, even while you're spinning it up, you can still use some of the power you're generating. That would just make it take longer to get up to speed. Yeah. All right. There you go. These are torque and moment of inertia problems. Hope that helps you solve some of the ones you have for homework.